Hello everyone. Today I want to talk about a physical phenomenon called convection. Convection is the vertical swirling of a fluid that's in a gravitational field when it's heated from underneath. So for example, if you have a beaker with water in it and you're heating it on a flame, let's make the flame red, that's flame. The heat goes through the bottom of the beaker and heats the water in the very bottom of the beaker. When you heat a fluid, you decrease its density because the molecules are moving faster and they bump into each other and move further apart. So it lowers the density of the fluid. So this lower density water that's at the bottom of the beaker becomes buoyant in the surrounding fluid because it's less dense. In the same way that a stick is buoyant in water because it's less dense than water. So it floats. So this is going to move up in the beaker. When it gets to the top, it'll cool, and you'll have vertical swirling like this. I have a demo of this phenomenon, which you'll see here. Here's a really nice convection demo. Just have this plastic container full of water. It has real nice flat sides. A screen. I'm heating a block here, a block of metal. And here's a LED pen light. It provides a very nice point source of light so that it makes a very clear silhouette of the water on the screen here. Now I'll just turn off the lights. And I'm going to put the block into the water. The convection is very, very clear. This will continue until the block cools down near the temperature of the water. So there's a simple example of convection on a small scale, but I wanted to show you some other examples of convection that exist in nature because it's a really important phenomenon in nature. If it wasn't for convection, we wouldn't have weather. If it wasn't for convection, the Earth wouldn't operate the way it does to make the surface of the Earth habitable. The sun would not operate the way it does, and in fact we wouldn't have the chemical elements for reasons having to do with, well, I'll explain. So let me show you some examples in nature. Well, here's the example that I just drew on the board, convection inside a pan of water. The coil heats the bottom of the pan. The water at the bottom of the pan becomes less dense and becomes buoyant in the surrounding water and so floats up and swirls like this. Another example of convection in nature that you've seen every day is in the Earth's atmosphere. Cumulus clouds, the kind of puffy clouds that you see on a partly cloudy day, where there's a cloud separated in space by other clouds. Each of those is a place where convection is occurring. The sunlight is heating the surface of the Earth, which heats the air above it, and that warm air becomes buoyant in the surrounding air of the atmosphere and begins to float upward. When that happens, the air rises and actually goes to higher altitude and expands because it's going to lower pressure. And as it expands, it cools, and gaseous water that exists in the air turns into droplets. It condenses into droplets, and those billions of tiny little droplets, that's what a cloud is. So the air is moving vertically. Every place where you see a cumulus cloud is a location where the air is moving vertically. As the air continues to move up, it moves into drier air. The droplets re-evaporate into a gaseous state, and then the air simply moves down. So a cumulus cloud is a location where convection is occurring. You know that it's not every day that you have partly cloudy, right? Some days it's clear, some days it's overcast. On clear days, the Earth is not being heated enough to cause this convective circulation, which is why you see partly cloudy conditions mostly in the afternoon, after the air heats up and the clouds begin to go So here's one very important example of convection in the atmosphere. Now, when there's a strong enough convection, these water droplets can grow and condense and become raindrops, and that's how rain occurs. It's a very similar phenomenon to the formation of a cloud, but a more extreme one. So here's a picture of a partly cloudy day. So here, this cloud, for instance, the air is moving up through it, out the top, and then going down between the clouds. So these clouds are always separated by some distance. That's where the air is moving back down toward the Earth. Another place where convection occurs is inside the Earth. So this is supposed to be the lithosphere of the Earth, the hard shell that's at the surface. Underneath that is a relatively molten mantle. The mantle it's a sort of a viscous fluid. It's not real thin like water, but it is fluid, especially the upper part, which is called the asthenosphere. And this is slowly undergoing convective motion. And you can see it's rising here and moving across here and sinking back in other places. This convective motion is what causes plate tectonics. This motion of the mantle material moves the tectonic plates laterally, and where there's convective motion upward, the new tectonic material is forming here and moving outward, and then the tectonic plates are subducting under each other and melting back into the mantle. So plate tectonics is caused by convection, and it's plate tectonics that's responsible for the existence of the continents. The Earth would be a big ocean if it weren't for plate tectonics, and it's also responsible for stabilizing the content of the Earth's atmosphere. So this is an example of convection inside the Earth that's very important for the habitability of the surface of the Earth. Here's a zoom up on here. Here's a part of the asthenosphere where the circulation's moving. So here's a spreading center where molten material is solidifying into lithospheric plate material. This blue is supposed to be oceanic plate. It's not the blue of the water, it's the plate underneath the water, but you can see it's spreading apart. The plates that are underneath the oceans are mostly lower. Well, they're all lower, which is why the water is there, than the plates that are underneath the continents. And you can see the oceanic plates are the ones that subduct under the continental plates and melt back into the lithosphere. Back into the mantle. It's this activity that causes volcanic activity, which produces more continental crust. So, for example, in the western United States, there's a whole string of volcanoes like Mount St. Helens and Mount Hood, and those are the result of a subduction of a tectonic plate underneath the North American plate, giving rise to that volcanism, making more continental crust. Another location of convection inside the Earth is in the core of the Earth. This is supposed to be the inner core of the Earth, which is solid iron, and this is supposed to be the outer core of the Earth, which is liquid iron. Now there's a lot of heat inside the Earth due to the decay of radioisotopes, and that heat is causing convective circulation to occur in the outer core. That, combined with the rotation of the Earth and the fact that iron is a very magnetic material, causes what's called the geodynamo, which generates the Earth's magnetic field. So here you see some magnetic field lines that have been generated with this. And of course the Earth's magnetic field is another thing that's responsible for the habitability of the surface of the Earth, because it deflects material from space like solar wind away from the atmosphere, and which, if it struck the atmosphere over time, would erode the content of the Earth's atmosphere and make the surface of the Earth uninhabitable. Convection is also very common on other planets. Here's Jupiter, and all the features that you see when you look at Jupiter are cloud features. There's really no surface to Jupiter, so all you're seeing is clouds. And here's a cross-section of what it's probably like. Convection's occurring and rising up in some places and sinking down in others. And where you see the white material, like these clouds, this is higher altitude stuff that you're seeing, and then the gas is moving down in these darker areas, which are actually looking at lower altitude. Those are thought to be the places where the air is moving back down, and here it's moving up. So the entire atmosphere of Jupiter is convecting and producing these magnificent patterns like this. And convection occurs inside the sun. The entire upper layer of the sun, something like 30% of the depth of the sun is convecting, and there's convective circulation. And that is part of what brings the energy that the sun produces in its core to the surface, and where it is radiated off into space. So it's very important for the operation of the sun. And in fact, if you take a photograph of the sun, this is a close-up picture of the sun, you can see these cells of convective heat. This is hot gas that's rising up, coming to the surface and cooling, and then it spills down in these darker areas where it flows back down. Some of these are thousands of miles across, so it's hard to get a scale on this picture because this is the sun, but this is convective cells at the surface of the sun. And in fact, most stars have strong convection of them. The sun's considered a low-mass star. It's mid-range in size between what we call high-mass stars and red dwarfs. And in the sun, convective circulation occurs in the upper layers. In heavier stars, convective circulation occurs on the inside and not on the outside. We know this from modeling of their interiors combined with observation of real stars. The lowest mass stars, called red dwarfs, have convective circulation throughout their interiors. One of the things that this causes for these stars is it circulates the material from inside to outside, which keeps it completely mixed up. The fuel that stars use to shine is hydrogen, basically protons, and because this is circulating up, those stars won't ever go dark until they completely run out of hydrogen, because it's always being mixed up. There's always more fuel being taken to the center. So that vastly extends the lifetimes of these things, which are already extremely long. There's also convection occurring late in the stage of a star like the sun. When it reaches a phase that's called the asymptotic giant branch stage, convective circulation mixes material, and then the star is also going through these pulsations late in its life as it's dying. The convective circulation causes material to mix and causes nuclear reactions that don't normally occur, which produces heavy elements. In fact, the elements of the bottom half of the periodic table, the really big elements like gold and silver and iodine and so forth, are partly produced in this process, and the pulsation chucks it out into space. So convection is responsible for the production of some of the elements that we have on the Earth. This, of course, took place in a generation of stars that came before the formation of the solar system. So here's convection producing elements. This is the remnant of a supernova, and convective circulation is also important in a supernova, and specifically when a heavy star reaches the end of its life, the core undergoes a collapse for reasons that have to do with relativity, and that releases a whole bunch of energy. That energy gets transferred to the outer layers and blows the star apart. The way it gets transferred to the outer layers is thought to be that there's extremely energetic convective circulation occurring in the collapsed core, and that brings the energy to the surface, where it's deposited to the rest of the star, blowing the star apart. This is also important for our existence because most of the elements of the periodic table actually come from these stars. They produce them during their lifetimes and during one of these explosions, and then blast them out into space, where they can be taken up in the formation of subsequent generations of stars, like the sun. And that's thought to be where we get most of the elements. Of course, the elements, 24 of them or more, are important for our own physiology, and probably most of the elements are important for the way the Earth functions. So here's another example of convection, how important it is to us. So there's just a few examples of convection in nature. You may never have heard of convection before, but it turns out it's a really important phenomenon. Thanks.